Hello and welcome to another review session for Calculus 3208 in your final exam, presented by CDLI, and we're looking at related rates still in this session, and we're just looking at some more unique related rate situations. So let's get right to it, and just more problem-solving situations here, nothing special to talk about. Let's just get right down to some examples. So we're going to start with a situation where we have a bicycle that is 4 kilometers east of an intersection. So let's say that our intersection is at a point right about here, and we have one bicycle that's 4 kilometers east of that point. Okay, and then we have another bicycle. Sorry, that one's traveling toward the intersection at 9 kilometers an hour, and at the same time we have another bicycle that is to the south, 3 kilometers south, and is traveling away from the intersection at 10 kilometers an hour. Okay, so we have one bicycle over here and one bicycle down there. And then it says, determine if the distance between the cyclists is increasing or decreasing. All right, so the distance between them will be a line like that. And so we can see here that we have a right triangle. This will be our right angle over here. And we have to determine some stuff about some related rates. So we know the first one is 4 kilometers away and is moving toward the intersection at a rate of 9 kilometers per hour. And the other bike is 3 kilometers away and is moving away from the intersection at a rate of 10 kilometers per hour. And so let's label some sides. Let's call this, the vertical one can be y and horizontal can be x. And then the distance between the two bikers, let's call that z. Alrighty, so if we put this stuff together, we can get a relationship between x, y, and z quite quickly. We can see that x squared plus y squared equals z squared as always. So we'll take the derivative of that implicitly, and we have 2x times dx over dt plus 2y times dy over dt, and all that is equal to 2z times dz over dt. All right, so then it becomes our job to eliminate these 2's that we have, make those go away, and let's see, we can fill in everything in that equation that we need. We have both speeds, and we have x and y here. But the only thing we don't know is z. But this is a right triangle, isn't it? Yeah. And at the time in question, when y is 3 and x is 4, I'm betting z is going to be 5 because that's a 3, 4, 5 Pythagorean triple. Alrighty, so we've got x is going to be 4 times dx over dt. Now, we said that bicycle x, I guess we'll call it, is moving at 9 kilometers an hour. But if it's getting closer to the intersection, its distance is actually decreasing. So we're going to say that this is negative 9 plus y's distance is 3, and it's moving at a rate of 10, and its side is getting longer as it moves away, so we'll leave that as positive 10. And that will be equal to z, and we don't know what's happening with z at this time, but we do know that its length is 5, and we're trying to figure out its rate of change, dz by dt. So dz by dt, if we sort of look at this equation backwards a little bit, we've got negative 9 times 4, so that's minus 36, plus 30 divided by 5. All right, so that tells us our rate of change, dz over dt, is going to be negative 6 over 5, and that is minus 1.2 kilometers per hour. Okay, so what does all that mean? Well, if z is shrinking with a negative rate of change, then they're moving closer together, which is one thing they asked us. And at what rate? Well, we just found it. About 1 1/5 of a kilometer every hour they get closer. Let's try another one. A spotlight on the ground shines on a wall that's 12 meters away. Okay, sounds like another triangle coming up here. Let's see, there's the ground, and then we'll put a vertical wall over here, unless we're in Pisa, but I don't think we are. And the wall is 12 meters away, so we'll say that this is 12. And we'll put our spotlight over here. I don't know, I'll draw a circle with some lines. Looks like the sun, only half of it. All right, so a man that's 2 meters tall walks from the spotlight toward the building. Okay, so let's put, this is going to be our man right here. That's a very detailed drawing of him. So he's going to walk from the spotlight toward the building, and looks like he's going to cast a shadow according to this problem. So this guy's going to cast a shadow over here on the building that will be yay tall. So there's a shadow on the building. All right, and we want to know if he is moving at a speed of 1.6 meters per second. So we can look at that in one of two ways. We can say that this side here is increasing at that rate, or that this side here is decreasing at that rate. And it matters not. I'm going to pick this one. I'm going to say that this side is x, and that dx over dt is going to be negative 4. or nope, negative 1.6, excuse me. So this is negative 1.6 meters per second. Okay. And we want to know how fast is the length of his shadow on the building decreasing. So if we call this, I don't know, let's say S for shadow, how fast is S shrinking? So the man is 2 meters tall. This is going to be X, and that makes this side over here the full length, which was 12, subtract the X that we had. All right, so let's set up an equation here, and I'm just trying to see a relationship. It's definitely not going to be Pythagoras with those two nested triangles there. Looks to me like we're looking at similar triangles. So we'll say 2 over 12 minus X should be equal to S over 12. Small triangle over big equals big triangle in terms of proportion. So if we cross multiply now, 2 times 12 is going to give us 24, and then we'll have 12S minus XS. We're doing this to excess tonight. So let's see what happens now. If we differentiate both sides, the derivative of 24 will be 0, and the derivative of 12S will be 12 times ds over dt. And then we're going to need a product rule for this stuff. So it's going to be x times ds over dt plus s times dx over dt using our product rule. And then we can distribute that negative sign and fill in some details. So let's get at that. If we distribute that and fill in the details at the same time, let's see, we're going to have 0 equals 12. ds over dt is the magic thing that we're looking for. And we're going to subtract. X, it says, at a time when he is 4 meters from the building, so X is going to be 4. And ds over dt is still what we're looking for. And we're going to have to add S, which is the length of his shadow at this particular time. Let's see, we're going to have to use our equation again to get that, aren't we? So from here, we can see that S will be equal to 12 times 2 over 12 minus 4. So that's going to be 1/4 of 12, which is 3. So at that particular time, his shadow is going to be 3 meters long. So this will give us, sorry, from down here, we were going to subtract, actually, S, which is now 3 times dx over dt. And we already said that x was a number that was going to be shrinking at a rate of negative 1.6 meters per second. So we put this stuff together and we have 8 times ds over dt should be equal to negative 3 times 1.6, which is negative 4.8. Okay, so then ds over dt is the rate at which the shadow's size is changing. That'll be negative 4.8 divided by 8, and that looks a lot like negative 0.6, because 6 8s are 48, and that was in meters per second. So yes, the shadow is in fact shrinking at about 60 centimeters every second. Good question. All right. Next one. An airplane is flying due east at a constant height of 16 kilometers, and it passes directly over an air control tower. Okay, so let's put our air control tower right here, and we'll initially have our airplane right there. So we'll call that the tower. And it says later the plane passes over a route marker which is 12 kilometers east of the tower. Okay, so east of the tower here, we're going to go 12 kilometers. So over here we've got 12, and this will be our route marker, so we'll call it M for marker. And let's draw a line to represent the fact that the plane says flies at a constant height of 16 meters. So anywhere we want to draw some lines across there, we got to remember that the distance between these two lines is always going to be 16 kilometers. Okay, now it says later the plane passes over a route marker, blah, 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 blah. Sorry, missed my spot. At this moment, the distance between the tower and the plane, so at the moment when it's crossing the route marker above that, the distance from the tower to the plane, so that's this distance, is changing at 400 kilometers per hour. So we better give that a name so we can call it a rate of change. So let's call that Z, and we'll say that dz over dt is going to be 400 kilometers per hour. It's going to be increasing as the plane is flying in this direction. Okay, so then it says how fast is the plane moving at this time? Okay, so I guess we can talk about the length of this side up here is x, and then I'll just draw a vertical like this, and then the rate at which the plane is moving will be our dx over dt. So we want to know what's dx over dt, at that particular time, if this side happens to be 16 constantly. And at the moment we're looking at it, we want to know this is going to occur when x is equal to 12, because that's the distance between where we saw the plane first and where it is when we measured that speed for z. So this is going to be a Pythagorean relationship here. X squared plus 16 squared will equal z squared. And differentiating, we have 2x by dx over dt plus 0 will be 2z by dz over dt. And again, the 2's are going to go away. It's a typical thing to happen with these. And we want dx over dt. And we're going to try to figure that out when we have z over x, if I divide both sides by x, times dz over dt. And so we want to figure all these things out when x is equal to 12. So we've got to know what z is at that same time, but we can see the right angle triangle relationship again. So I'll use Pythagorean theorem, or recognize this as a 3, 4, 5 triangle if this side has a length of 20. So this will be 20 over x, which has a length of 12, times dz over dt, which we already knew was 400. So what we should have is 20 over 12 times 400. So that's the same as us having, let's see, 20 over 12 is like 5 over 3 times 400. What's that going to give us? Let's see. 5 times 400 divided by 3 is 667. Roughly 667 kilometers per hour. That's a pretty fast moving plane, I do say. So that's how we solved that one. Good question again. Alrighty. Next is the your turn question. So have a read through it, see if you can figure out some stuff. And I'll jump to the solution slide. So here is your solution. And hopefully you're getting this correct. And if not, you're figuring out what it is that you're doing incorrectly so that you can fix it for next time. And we'll just take a quick run through of some of the key ideas that we saw in this session. So the first thing we notice is that to solve a related rates problem, we need to find the mathematical equation that relates the variables. Sometimes we need a secondary relationship. We differentiate implicitly with respect to time. We determine any required but yet unknown quantities, like the values that we get in Pythagorean theorem later on. And we fill the information into the differentiated equation to find the required value. Hope that's helpful. Hope your studying's going well, and good luck with your calculus.